So as I said, you've got your, in your y equals, you've got your 1000 times 1.15 to the power of x, and in your y2, you've got what it's set equal to. Right, and then what we needed to do is to graph it. So graph, and remember, like when we graph it, that we can't actually see anything right now. As I said, the reason why you can't see it, oh my goodness. So the reason why you can't see it is because of this 10,000. Your y max, whatever it's set equal to, like whatever is in your y2, for example, your y max has to be above that, because this function here is just a horizontal line that cuts through y equals 10,000. So we can't see it on here. So let's go to the window and we'll adjust our y max to begin with. Y max, let's go down to y max. Y max, make it a bit bigger than 10,000, like maybe make it 10,500 or 11,000. Just experiment a bit is what you want to do. Then graph, let's see what we can see now. Can we see anything? Yep, we can start to see the function is forming. So here's the exponential function. What you're seeing in blue is 1000 multiplied by 1.15 to the power of x. And here is the horizontal line, which is y equals 10,000. We can't see the intersect, so we're going to have to make our x max bigger so that we can see out here somewhere. So let's go window, x max. It's currently on 10. Maybe let's go up to 30 and see if that enables us to see the intersect. Your x max normally is something like 100 or less. So you don't want to be putting in like 10,000 or anything for x max. Y max sometimes is quite big. Yeah, so we can see that when the red line is plotted, we're going to see the intersect now, like we've gone far enough this way. Excellent. So we need this little intersection point here so that we can find what value of x matches this particular coordinate, this particular equation. So second calc, intersect, select number 5. First curve, you just press enter, it's on the first curve. Second curve, press enter because it's on the second curve. Guess, yes, we'd like you to guess, please, calculator. Here's our intersect. So our coordinates, rounded to 3 sig figs, are, is that 16.4, is it? Have I got the right thing in here? 16.4 and 10,000. I'm not 100% sure. I've got, on my answers, I've got 14.9. So I'm just wondering why I've got a different one here. Let's check that I put the right function in. So y1 equals, perhaps my original answer was wrong, 1000 multiplied by 1.15 to the power of x. So I've got that, equals 10,000. So perhaps my answer that I had in here was wrong. Let's just do a second calc, intersect, 1, 2, 3. Initially on my answers I had 14.9 rounded to 3 sig figs. So if you are getting 14.9 and a different answer to me, that means I've done something wrong right now. So, but if you are getting the same answer as me and you agree that we've done it correctly, then this is what the correct answer should be. So it looks like it's 16.47 something. So about 16.5. So I had 14.9, but no, don't worry, I do have the right answer. I don't know what I'm talking about. So I do have the right answer, which is 16.5 weeks, which does match. So 16.5 weeks, because we don't want the y coordinate. It's asking for the x coordinate, because that's our x. So after 16.5 weeks, then the amount of grasshoppers, the area eaten by grasshoppers, will be around 10,000. So they're saying, how long will it take for the area to be affected to reach 10,000? That's what we found. 16.5 weeks is how long it takes for the area eaten and affected by grasshoppers to be that. Let's move on to the next one. Decay. So remember I was talking about like real life problems to do with exponential functions. You have exponential decay, which goes down like this, and exponential growth, which goes up like that. Let's see this decay problem. What is it? Consider a radioactive substance with original weight 20 grams. So that's why you can see at time 0 we have 20 grams here. It decays by 5% each year. So it's going down by 5% each year. The multiplier therefore is 95%, or 0.95. So the way that was kind of worked out is because it's going down by 5%, you can go say 100 minus 5% is 95%, and turn 95 into a percent into a decimal, you divide by 100. So because 95%, because as you decrease, it's 95% of what it was. So that's why the multiplier is 0.95. and so on. So here that we kind of worked out some different points. Okay, times 0, sub it in, you get that, and so on. We end up with a little function down here basically, so it's trying to point out that you're getting a function. W stands for the weight. What does N stand for? The number of years. Equals 20 because that's the original weight. So the original weight should be what we have here, multiplied by the multiplier 0.95 because it's decreasing by 5%. So that means that the multiplier is 0.95. If it was increasing by 5%, the multiplier would be 1.05 because 105%. To the power of n, so that's our x there. So from the equation above, where does the 20 come from? So as I said, 20, the 20 in here was the original weight. Original weight 20 grams. So you can write it is the initial weight or original weight of the substance. You can also specify it's at time n equals 0. You get that value. So it's the original weight or the initial weight of the substance at time equals 0. Where does the 0.95 come from? So I did mention it before, how we calculated it, but we should maybe take a note of it. So as the weight is decreasing as opposed to increasing by 5% each year, the rate or the multiplier, so the rate is, the way we work it out, remember we do 100 minus 5 gives you the 95% because it's decreasing, as opposed to increasing, which would be 100 plus 5. Gives you what the percentage would be, 95%, but you've got to turn it into a decimal to put it into the equation. So turn to a decimal, divide by 100. You get 95 over 100 is 0.95. So make a note of this. This is important to write this down. Because sometimes you're expected to work out the rate yourself. Sometimes you're just given it in the question. Let's do another little example like that, where we might have to calculate a rate, although it's been done here. When medication is taken by a patient, it's slowly used in the body. So after 2 hours, the amount of drug remaining in the body is given by the amount of drug with respect to the time is equal to 120, which clearly must be the original dose, multiplied by 0.9, which must be the rate, to the power of t. Milligrams, that's meant to stand for mg. So try to think 120, what does it stand for? It's the original amount of drug in your blood when they first inject it into you. That's the original amount of drug. 0.9 is the rate. So try to think, does that mean an increase or a decrease? If it's less, the rate is less than 1, it's a decrease. If the rate is more than 1, it was an increase. So what's that as a decimal? 0.90. So that means like 90%, which is a 10% decrease from 100%. If it was 0.8, that would mean a 20% decrease, because 80 is 20 less than 100, and so on. So back to here. Find the amount of drug when time is 0, 4, 12, and 24 hours. So obviously at time is 0, if you plugged in 0, you can always check it out by plugging in 0 into the equation and calculating what it is. You get 120 though. You can see from the equation what the original one is. At 4, what you would need to do is you'd need to plug it in. So show you working out. Make sure you do that, like I did 120 times 0.9 to the 0 to work out that one. At time equals 4 hours, it's 120 times 0.9 to the power of 4. So 120 times 0.9 to the power of 4, you get 78.7. At time equals 12 hours, similarly, 120 times 0.9 to the power of 12 is the exponent. Should give you 33.9, that's the next one. And the last one, 24 hours. So you'll do 120 times 0.9 to the power of 24. Plug it in your calculator, you should get 9.57, rounded to 3 sig figs. Milligrams, don't forget your units. We're talking about the amount of drug. The amount of drug is in milligrams, it says. What was the original drug dose? We've already talked about that. It was 120, so feel free to do that. Don't forget your units, milligrams, 120 milligrams. Graph the amount of drug against time for time is greater than 0. So your window, your x max has to be kind of from 0. I mean your y x min would be from 0 onwards, greater than 0. Use the information from A. So you can just plot the points. So that's what I did. So we're kind of going for, it's decaying. So it's starting at 120 and it's decaying. So we need our x-axis to go up to 120 because it's going to go down from there. And they want to go up to about 24 hours. So let's do that on our y-axis. That was our y-axis. And our x-axis should go up to 24. If you're not sure what, you can't see what I've written, fair enough. What I've written here is 4. I've gone up by 4s. 4, 8, 12, 16, 20, 24, and you should label this time with respect to hours, and you should label this D with amount of drug in milligrams. Plot the first point, 120. At 4, we've got the point 80, roughly, 78.7. At 12 hours, 33.9. Is that? There it is, 33.9. And at 24 hours, 9.57. Plot those 4 points, because they told us to use the information in A, and then just draw a smooth curve through them. So that's what they wanted us to do. Lovely. That was C. Now D. Use the graph or technology to find when there is only 25 milligrams of drug left in the body. So my graph's a bit dodgy to do because 25 milligrams, it's a bit hard to read. So I went up like 20, 40, 60, 80, 100, 120. So 25 would be about here. You could, if you had a really nicely drawn graph on graph paper, like in your exams, you could read across and go down. But mine's not a very accurate graph, so I should really do it with calculator. First step, they want us to say, they want to set the drug equal to 25 and the equation on that side. So let's write the equation. 120 times 0.9 to the power of t equals 25, because I'll get a method mark for doing that. And now, unfortunately, we don't know how to use logarithms in math studies, so we have to use graphing to solve for an unknown exponent, because it's not one that we can just rearrange or anything like that. So go to y equals, clear what you've got in there, make sure everything else is out. Let's put in our equation. 120 multiplied by, you can use the brackets if you want, you don't have to though, 0.9, always good to try though, to the power of x, and we've got it set equal to 25. So let's graph, and remember we've got the crazy kind of settings from the previous question up to 11,000, so that is probably why we're not seeing anything really going on, because everything's really going on down here. So always good to just go back to Zoom standard, just resets it back to -10 to 10, -10 to 10. Unfortunately, we can't really see anything going on. And why is that? We need our y max to be greater than 25. So go to your window, calculator. Oh, it's still trying to graph. So see it's spinning here, it's still trying to graph the function that I've plugged in. So we just have to be nice and patient and wait. So our, basically, and when we go to window, our y max is going to have to be greater than this, so maybe put in 30. The time might be more than 10, so we might need to adjust that, but I tend to adjust the y max first, and then if I need to adjust the x, then I do it after that. Oh, it's taking a very long time. Alright, so I'll give you a clue though. Ah, I see why I was confused before. Oops, it's disappeared. Okay, still taking too long. If you make, basically you're going to need to make your y max about 25 in your window, and you'll find that the x, you still don't see the intersect because it's going to be greater than 10. This is the one, sorry, that ends up equaling 14.9, not the previous page. So 14.9 is what you should get. So you're going to graph it, and of course when you adjust your y max to be 30, adjust your x max to be about 20, and then you'll see the intersect. And then you'll go second calc intersect, enter, enter, enter. And to 3 sig figs, you should get 14.9 hours. This one's just taking way too long. So maybe I can just, can I switch the calculator off and just start again? Oh, okay, now I can do it. I'll do it just for the sake of showing you. Y max 30. And I told you already that the x max is going to have to be about 20. Because when you do 10, you don't see the intersect still. But hopefully it won't take so long to graph this time. It is still taking a long time though. Here we go. Oh my goodness. But it doesn't matter, we don't see the graph that well. The graph's kind of a big decay because it starts at 120. So that's why we can't see the top part of it. I just went up to above the intersect. We are only interested in the intersect anyway. If you wanted to adjust it, you could. You could make the x max, sorry, the y max greater than 120 if you like 130, and then you can see the whole graph a bit better, just so you understand what's going on. Maybe to find the intersect, you could have just gone second calc intersect. Sometimes it's good to zoom out a little bit like this, because maybe there was more than one intersect, but in this case there's not. There's just this little one here. So it started at 120 and decayed. Let's see when it crosses the 25 line. So go second calc, second calc, yep. Intersect, which is the fifth one. Enter, enter, enter. There it is. So what do we have? We have 14.8 blah blah. So 14.9 is the x value. And that represents a time, 14.9 hours. Now we're on to last page for the lesson. Another example. 6 pairs of bears were introduced to a large island off Alaska, where previously there were no bears. It is expected that the population will increase by 14% each year after the introduction. So this is an interesting one where you're going to have to find the rate yourself. Find the model for the number of bears on the island T years after introduction. So 14%, it's an increase. So what's 100 plus 14%? It's 114%. What's that as a decimal? You divide by 100. It'll be 1.14. So let's show the working out for that. The rate will be 100 plus 14, then divide by 100. Your rate will be 1.14. Remember the function, they said b with respect to t, so b brackets t equals. But remember, you've got to start with, before the rate, you write what the original population was. So what was the original population? 6 bears. That might have been hard to see because it was written in words. 6 bears was the original population times the rate. And the rate to the power of t. T with respect to, that's the number of, what was it, number of years or weeks? Years, I think it is. So that's our model. B with respect to t, the number of bears with respect to time, is equal to the original population multiplied by the rate, which is 1.14, because it's a 14% increase. If it was a decrease, we would have a minus right there, to the power of t. Now, question B, find the bear population after 7 years. That's really nice and easy. All you have to do is substitute in the number 7 and calculate the answer. But you really will not really get many marks unless you don't show your working out, unless you show your working out. So go 6 times 1.14 to the power of 7, plug that in your calculator, and it rounds to, write the unrounded answer first if there is one, and then round it to 3 sig figs, 15.0 bears. So after 7 years, we expect there to be 15 bears as opposed to 6 bears. It takes a very long time for them to grow in population. C, how long will it take for the population to reach 100? So this is going to be a solving on calculation, because we've got to, by calculation, we've got to substitute in 100 here, set it equal to that, and solve for t, because we want to know how long. So make sure to show that so you get your method mark. 6 times 1.14 to the power of t, because we don't know what t is, equals 100, because they said population to reach 100. We have to plug this into our calculator now. Let's go y equals. Let's clear what's in there. Let's put in the new model, which was 6 multiplied by. Put the rate in brackets if you want, but it's a positive rate, so to be honest, you don't have to the power of x, set equal to 100. You might realize already that clearly your y max has to be greater than 100. You might have gotten the hang of that already. X max is normally somewhere a bit less than 100, so I've currently got it at 20. So what's interesting is I've got to make my X max bigger. If you were on Zoom Standard, you would not see this intersect, because I happen to have my X max on 120 from the previous question. So that's why I don't need to adjust it. It's because my Y max is already greater than 100. It's 120. But my X max at the moment is on 20 from the previous question, but clearly the intersect is higher than that. So or further along. Let's make our X max more like 30. So clearly it's going to be more than 20 years. Makes sense. It takes a long time for the population of bears to reach 100. I wouldn't expect it to be just a few years. So it's good to think critically about the answers. Do they make sense? So you know if you've done something wrong. We can see the intersect, so now we're ready to calculate it. Second calc intersect, which is number 5. Press enter 3 times. Enter, enter, enter. Ta-da! There it is. So we want to know the time, which is the x-coordinate. We already know that it's set equal to 100. What would that be? Write that out unrounded first, and then round to 3 sig figs. What would that be to 3 sig figs? 21.5, because next to the 4 is a 7. So 21 time equals 21.5 years before the population reaches 1,000. Great, that answer's finished. Last one, and it's about turtles. The population of turtles in a lake decreases by 7% each year, which is quite sad. There must be some disturbance there interfering with their growth. So it decreases, so the rate is going to be 100 minus 7, which is 93, and as a decimal it'll be 0.93. In 2005 there were 340 turtles, so clearly that's our original population. Find an exponential model for the number of turtles, t, in the lake after n years. So the number of turtles, t, so we should rate, oh well, sorry, I'm showing the calculation for the rate first. So rate equals 100 minus 7, which is 93, divided by 100. So equals 0.93, that's the rate. Good idea to do that first. And then underneath that, sorry if I got that here. Oh, here it is, it's over here. So the amount of turtles in the lake, t, and I happened to put in, you could have just said t equals because that's what they wrote, but I did t brackets n because it's t with respect to the number of years, or is it week? Yep, number of years, is equal to the original population, which was 340. So write your original population, 340. It's always multiplied by, for these exponential equations, multiplied by the rate, which is 0.93, to the power of t. Sorry, power of n, sorry about that. Capital T for the number of turtles is equal to the original population multiplied by the rate, which is 0.93, to the power of n, which is the number of years. How many turtles were in the lake in 2010? You've got to think, how many years is that? So initially it was 2005. So how many years do we need to plug into our equation? Oh, sorry, no, B. Back to here. Graph your model from A. So graph your model from A. The initial population was 340 and it's decreasing. So your y-axis has to go up to 340. So I'm doing it very roughly. So I just went up by hundreds. 100, 200, 300, 400. And this says T brackets N because it's the total number of turtles with respect to the number of years. Alrighty, and let's see. I went up to about 20 years. It doesn't tell you how many years to go up to, but I just went up to 20 years. No, I went further, didn't I? I went up to 30, just to be on the safe side. So you can see I'm going across 5, 10, 15, 20, 25, 30, and that's n, the number of years. Yeah, so what you can do is you can calculate a few little points if you like. So you could try subbing in some values, or you can kind of just, as you know, it decays. So it starts at 340. You could have plugged in 5 after 5 years. What does it get? So I just, on my calculator, plugged in a few points. I subbed in n equals 5, got that answer, like that height there. Plugged in n equals 10, worked out that point. Plugged in n equals 30, worked out that point. Just to be on the safe side. You know it decays, starts at 340 and decays, but you're not sure, does it decay really rapidly? Does it decay super slowly? Kind of like in the middle. So having a few points plotted and calculated is a good idea. Alright, so that's our graph. See how many turtles were in the lake in 2010. So let's see. So in 2010, how many, from 2005 to 2010, how many years has that been? It's been 5 years. So plug in 5 years, 340 multiplied by 0.93 to the power of 5. Plug it in your calculator, see what you get. You get 237 turtles, round to 3 sig figs. And last question, D. If the population falls as low as 10, so meaning that the population is set equal to 10, conservationists will not be able to save the turtle colony, like they won't be able to breed any longer. According to your model, when does this occur? So it's one where we have to set this equation equal to 10 and solve for n. So again, you've got to show the substitution, write the model, set it equal to 10 because that's a very important minimum. I get 1 or 2 marks for that. And then you've just got to solve it on your calculator. So you go to y equals, leave whatever's in there. Make sure you're kind of like trying it out with your calculator yourself while we're doing all this. Plug in your model, 340 multiplied by the rate, 0.93. You can put the rate in brackets if you want. To the power of x, and equals 10. Graph. So again, my settings on my window are just from the previous one still. Might take a long time to graph as a result. Still spinning, so if yours is spinning, don't worry, it's still just calculating for you. So we can't see at the moment. So 340 is the original population. So in a way, my Ymax has to be greater than 340. So Ymax has to be greater than 340 because it starts there. So actually, to be honest, just has to be out here really. So, but no, I don't need to make it greater than 340, but I'm going to do that just to show you the graph. So I'm going to make my Ymax about 400, just so you can see the graph a bit better. Confirm, it's a good thing too, because it confirms the graph that you've got kind of looks correct. And come back graph, there you are. But we still won't be able to see the intersect, because the intersect actually is out here somewhere. So we're going, what do we have to adjust in the window? We have to adjust the X max, make the X axis go out a bit longer. So maybe you want to go out to 30 or something. What have I currently got it on? Let's see. X max is 30, so no, we want to go higher than that. Let's go 50, because I just don't want to do 40 and then have to do it again. So 50, hopefully for sure. It's not going to be more than 50 years. Quite often the X max doesn't have to go beyond 100, but I have seen a question where you had to go up to 200. Hopefully we can see the intersect. Let's see. If you're not sure, just go second calc, intersect 5, go enter, enter, enter. Does the intersect show up? Yes, it does. So we do see the intersect. The intersect is at 48.592.075. So write the unrounded answer and then round your answer to 3 sig figs. That'll be 48.6. So what was this asking again? It was asking for the number of years to solve for n. So 48.6 years is how long it takes for the population to fall as low as 10 turtles. And after that, the conservationists can't save them anymore because there's not enough turtles to breed and continue on with the colony. So this is showing you some nice real-life applications of this kind of math. Okay, that's the end of the lesson.